Okay, welcome ladies and gentlemen to Unit 3, Lesson 3, Differentiability. So we're going to figure out where a function is not differentiable or if a function is differentiable at certain points. And we're going to learn another one of our humongous theorems right here towards the end of the lesson. So let's go ahead and begin. We're even going to figure out how to use our calculator today too. There are a few different spots where a function might not have a derivative. So f prime of a might fail to exist. We may have noticed one from the last lesson, and oops, sorry about that. One of the last lessons we were dealing with drawing derivatives, or drawing the function from the derivative. And you recall the function that kind of went like this and like this. You notice that there was no slope at x equals 0, which actually meant that the derivative didn't exist at 0. And if you recall what that graph looked like, is it looked a little bit something like this. And it had to do with that point right there. And we're going to call that point a name in just a minute. So essentially, if the slopes of the secant lines fail to approach a limit as h approaches 0. So the first one we're going to look at is a thing called a corner. And that would be something like the absolute value function like that I graphed right there. That just shows that that corner has no derivative. It has no slope at that point because the slope of the left side is -2 and the slope on the right side is +2 or whatever. And they're not the same, so the limits don't approach the same value. We also have these ideas called cusps. And that would be like a graph of x to the 2/3. Be something like this and something like this. This little corner right there is not a corner because a corner would be this, where the 2/3 comes down here like this and then bounces back up like that. So it'd be called a cusp. So here we have corners, here we have cusps. There's no derivative at that point. There's a derivative everywhere else except for that point. We also have problems with vertical tangents. The graph of x to the 1/3, or the cube root of x, is actually kind of deceiving. It looks like there should always be a derivative. It looks like there should be a slope at every single one of these points. However, right here, this goes from being very, 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 very positive to going less positive in the other direction as a slope. Right here is actually a vertical tangent. Because if you were to try to do the limit definition at 0, the limit as h approaches 0 of cube root of x plus 0 minus the cube root of 0 all over h, it would end up not working. That whole limit definition of the cube root of x does not work. You would actually end up with an infinity, I believe, in this case, and so therefore infinity would not be an actual tangent slope. Or on any points of discontinuity. One of the problems from yesterday's or the previous lesson was a graph that looked like this. The graph came down here like this and stopped, and the other line went like this. Now the slope on the left was 2 and the slope on the right was 2, but because there's that point of discontinuity, the limit, the right-hand derivative, is non-existent. The right-hand derivative had no value coming down to that point right there, that open dot. So that meant our discontinuity created a non-derivative. So you cannot find the derivative at whatever that x value was. Let's say that x value was at 1. All right, so those are the times when f prime of a might not work. I know on every single one of these I put a at x equals 0, but that's not always the case. I could move these around wherever I wanted to. And each of these types of functions have no derivative at that individual point. And you basically would show the fact that the left-hand derivative and the right-hand derivative are not the same value, or does not exist like this cube root function. All right, I have mixed emotions on the calculator. The calculator is handy. However, it sometimes gets overused. Now, basically, if I want to say f of x is equal to, let's say it's a function that we don't know how to find the derivative of yet. And I wanted to find, hey, what is f prime of 7? If you go to math and hit the number 8, we just start calling it math 8, by the way, because once you get familiar with it, math 8, you know what I mean when I say math 8. But you click math on your calculator and you go down to number 8. It says in deriv with a parentheses. That's numerical derivative, which means I can find the derivative at a single point. And this is what comes up on your screen since most of you have the newer operating systems for your calculators. Just type this in here. And this is what's going to show up on your screen. This box right here is x, or whatever variable you end up using. Usually it's x. And as soon as you fill that in for x, this box becomes an x. This is your function. So I could type in this function. I might as well do it since I have my calculator here in front of me, I mean. 3x divided by x squared plus 7x plus 3. Oops. And then you notice I haven't done anything with that 7. This little bar in math says evaluate when x equals, in this case, the 7. And if I plug in 7, it will tell me that this answer is equal to negative 0.0135 blah, blah, blah. And the numerical derivative works pretty good. Math 9 works pretty good. It will come in very handy for us later, so you want to be able to use it. The syntax, the way the book tells you to plug things in, is a little bit different because it's an older version and it doesn't know about this new operating system. So this is what this is going to be for our calculators. All right, one of the things that go along with differentiability means the function is differentiable. You can find the derivative of it. If f has a derivative at the value a, then f is continuous at x equals a. We looked at this backwards the other day. We said that if the function is continuous, then the function is differentiable. But that's not always the case because those little points where the slope is different on the left than it is on the right. So this is actually our good definition. We may not have fully said that before, but this is saying, okay, if you have a derivative at a point, then the function is continuous at that point. So differentiable implies continuous. But continuity does not imply differentiability. Be careful there. All right, this is our humongous theorem. This is another one of those theorems that will show up on the AP exam. This is the IVT, the Intermediate Value Theorem for Derivatives. Let's get through the words, and then I'll show you the picture, what this represents. If A and B are any 2 points in an interval on which f is differentiable, which means continuous, then f prime takes on every value between f prime of A and f prime of B. So the question is, what does that even mean? So let's take a look at what that could mean. If I was to have some function being differentiable and continuous between A and B, opening up my textbook to that section so I draw the picture correctly. Sometimes I mess it up. So this is basically saying, if, like I said, if A and B are 2 points on an interval which f is differentiable, then f prime takes on every value between f prime of A and f prime of B. So if basically f prime of A is equal to 1 and f prime of B is equal to 10, and I want to know, is there an f prime of C, and I write A, is there an f prime of C that equals 6? So that's my question. Is there some C value whose slope is 6? Well, the case is yes, because if the slope is 1 at A and slope is 10 at B, some point in time there had to be some C value whose slope is 6. That's basically what it's saying. And again, it's another one of those existence theorems, but it means you could actually find it. If I told you f prime of A is 1 and f prime of B is 10, and I'm asking the question, find the C value that makes the derivative equal to 6, you can actually do it. But if I said f prime of C is equal to 11, C equals what? You're not guaranteed that that C value exists. It could, but you're not guaranteed that it exists. All right, that is actually about it for us. I'm going to leave you with this. I hope you enjoy it. I will see you guys tomorrow.